Thank you very much, Jayon, for this kind invitation. I'm glad to give this talk here to Kios. It's unfortunately impossible to visit you in person, but I'm very happy to give this talk also remotely. So this is on mainly G-2 and physics beyond the standard model. The talk will give quite an extensive overview and also brief recap of the standard model theory. And then I will focus mostly on physics beyond the standard model explanations of the G-2 result, where I will begin with quite a extensive set of general remarks on the situation, which are model independent. Then I will give a few examples of concrete models and constraints which can be placed on them. And finally, I will conclude with a few general lessons and an outlook. So I guess everybody has seen this famous plot from the Fermilab G-2 collaboration, where you see the result that was announced 2 weeks ago from the Fermilab G-2 experiment. And the first very important statement to make is that it agrees really perfectly with the previous Brookhaven G-2 determination. It's all within 1 sigma after so many changes to the experiment and so many checks. The result is really in very good agreement, and the world average now has a 4.2 sigma discrepancy from the standard model theory prediction, and could be due to new physics, of course, which is what we want to discuss today. Let's begin with the standard model of particle physics. The standard model is, of course, our theory in elementary particle physics, and it's maybe one of the best theories in physics. And it's really an old theory. It's almost 50 years old. And in all these 50 years, it has been confirmed over and over again in a multitude of many, many different experiments. The standard model is a deeply rooted theory. It describes all known interactions except gravity. It is a relativistic quantum field theory, which is based on fundamental principles. It is renormalizable, has a finite number of free parameters, mathematically consistent. It rests on the principle of gauge invariance, which means that the interactions between all the different particles are interrelated and very strongly constrained. It uses the concept of electroweak symmetry breaking spontaneously, which leads to the Higgs field, the Higgs boson, and the Higgs mechanism, which again gives rise to specific correlations between the interactions. And all these predictions from relativity, from gauge invariance, from spontaneous symmetry breaking, they are all confirmed by experiments. Now, G-2 or A mu is this unique single and simple quantity, a simple number, which is sensitive to all particles and all forces that we know via quantum fluctuations. So this is why it is such an interesting quantity. So let me explain this just very briefly. Quantum mechanics, of course, can be understood very nicely by looking at the double slit experiment. And according to Feynman, what we simply need to think about is that if a process can happen in several different ways or paths, then each path, the first slit or the second slit, contributes some probability amplitude, and the probability amplitudes are complex. They can interfere. And what we then observe is the interference pattern. So all paths contribute, and here in the double slit experiment, both paths contribute equally, of course. But imagine you drill a third slit in green here very far away, then this will also contribute. If it's thin and far away, it might contribute just a little bit, but it will also change the interference pattern. So all paths contribute. So for G-2, our paths are the Feynman diagrams. What we need to make sure is that the muon couples to the magnetic field in the experiment, and it can do so either directly or via the exchange of virtual particles. And so pictorially in the Feynman diagrams, we have the tree-level Feynman diagram, where the muon couples directly. This corresponds also to the Dirac equation, or you could say a point-like interaction. And the calculation gives G equal to exactly. Then there are loop corrections. The Schwinger diagram is the simplest diagram. It's also already very long time well known. And this is what we would call a quantum fluctuation, where the muon exchanges first a photon, then reabsorbs it later, and in the meantime interacts with a magnetic field. So you could also say this is now a non-point-like modification of the interaction, and it gives rise to the famous alpha over 2 pi modification. Technically, you can describe all these Feynman diagrams in terms of effective Lagrangians and effective Hamiltonians, and if you derive them from the Feynman diagrams in usual ways, then you can read off g minus 2. So I said all particles contribute, and so let me just give you the opposite end of the spectrum. The Schwinger diagram is the largest effect. So here is one of the most exotic effects in the standard model, where the two heaviest particles contribute that we know, the Higgs and the top simultaneously. So the muon would come along from the bottom, then emit a Higgs boson, which is extremely unlikely, of course, because the Higgs is so heavy. Then the Higgs dissociates into a top anti-top pair, and the top quark then interacts with a magnetic field. So this is an extremely exotic Feynman diagram, and many of you know this. This is a bar Z type Feynman diagram, and it contributes minus 1.5 times 10 to the minus 11. So it's an incredibly small modification, but it's non-zero, and this just illustrates that everything contributes. Let me also show you this simple-minded comparison between the G factors of 3 spin 1/2 particles. So if you imagine yourself 100 years ago or 50 years ago, then you would only know maybe the Dirac equation, and you see 3 spin 1/2 fermions. At one point, the proton was also considered elementary. Then the electron, muon, and proton at first glance look the same. And you see here from the G factors that the G factors are such a detailed probe into the inner structure of the particles, because the proton has now a G of 5 instead of 2, which means that these G minus 2 corrections are incredibly large. They are 100% or more than 100% corrections. And the reason is, of course, that the proton is a strongly interacting bound state. Whereas you see immediately that the muon is a heavy cousin of the electron. They behave essentially in the same way. And now, of course, we know that the reason is that they are both leptons of the first and second generation, which have almost the same interactions, but not exactly the same. But the muon is more sensitive to the fluctuations of heavy particles, and that is why its G factor is a little bit larger. And this is also why the muon is more interesting for us in particle physics, because it is a better probe of potential physics beyond the standard model. So let me now describe the current theory prediction from within the standard model. This comes from the theory initiative, which is a worldwide initiative with more than 100 authors. It was established a few years ago. There were already many workshops, and the theory initiative has the goal to publish each time before the experiment gives a new result, the current standard model theory prediction. And its attitude is to do it in a conservative way by taking into account all the approaches and all the knowledge which is available at the time. So the white paper from last year put forward the number that you see at the top. Actually, okay, I'm sorry, misprint. That what you see here is the experimental value. Sorry, I failed to exchange this. I noticed it yesterday, but I forgot to exchange it. I'm sorry. So the number is, of course, 181 at the end, with an error of 4.3 times 10 to the minus 10, which gives rise to the deviation we saw before. And the evaluation that goes into this number is an incredibly complicated calculation, which you can use basically to teach quantum field theory, because essentially all conceivable quantum field theory methods and tricks are used in getting this number. So let me just give you some few highlights. So of course, the most important contribution are from QED. And here we need 4-loop and up to 5-loop Feynman diagrams. This is an exercise in multi-loop perturbation theory, gives rise to interest in mathematics of Feynman integrals, evaluated using analytical new mathematical functions and numerical integrations. Then the weak interaction contributions are also very important and have been calculated at a two-loop level, also using perturbation theory. And that was actually the first electroweak full two-loop calculation in the standard model. Here also interesting renormalization group and effective field theory methods are in use in order to further increase the precision of those. Then there are these two kinds of hadronic contributions from what we call hadronic vacuum polarization, where we have a hadron blob in the photon propagator, and light-by-light contributions with a hadronic blob in a 4-photon green function. And they cannot be computed using perturbation theory, but we need other methods, and methods are available. So the vacuum polarization contributions are evaluated what we call dispersion relations. So these are exact relationships coming from relativistic quantum field theory, where one combines unitarity and causality to obtain these exact relationships between loop graphs, like we see in the g-2 diagrams, and experimental data for E plus E minus 2 hadron scattering. So basically, we can now replace the calculation of the Feynman diagrams by plugging in measurements from E plus E minus 2 hadrons at low energies. And those experiments are not so well known, but they are extremely important. And there are many of them using different methods. And from those experimental data come the predictions for these vacuum polarization. And the precision, as you see, is better than 1%. And that is a reflection of the experimental precision. There is also lattice QCD calculations coming along recently. There is impressive progress, but this is not yet used in this theory initiative prediction, but it most likely will be used in the future. Then there are these hadronic light-by-light corrections, which are somehow an even more difficult quantum field theory non-perturbative problem because of the many different energy scales which are simultaneously involved. And they can be calculated in 3 different ways. One also has the dispersion relations since recently. One has lattice QCD, and one also can use low energy hadronic models, which are not exact effective field theories, but models of hadronic effects. And but all these 3 different ways give rise to consistent results. And in particular, because of the dispersion relations, one has now quite a good control over the uncertainty. So all of this is the theory prediction in the standard model giving rise to this 4.2 sigma deviation. So let me now come to physics beyond the standard model, and first let's focus on some general remarks. G-2 has really some distinctive properties which are the cause of why it is so interesting, and I will give you also a brief overview of the analytical behavior of different kinds of model predictions before coming to specific examples. So we have looked at this picture before, and but actually, of course, the standard model, despite its success, leaves open quite relevant questions. For example, there are observational facts like dark matter. Dark matter must exist, but it's not part of the standard model, so we need to go beyond to understand dark matter. Furthermore, there are conceptual questions like looking at the schematics. You can ask yourself, why are there 3 generations of quarks and leptons? Why are there quarks and leptons in the first place? Technically, they are described by Yukawa matrices in the standard model. So you could also ask, what is the origin of those Yukawa matrices and their values potentially? Then we have 3 generations of quarks and leptons, but only a single Higgs. So is that true? There may be several Higgs bosons, several Higgs fields. And at any rate, what is the dynamics that gives rise to the Mexican head structure of the Higgs potential? What is the origin of electroweak symmetry breaking? So we would like to get answers to all these questions. And as you know, this is an incomplete list of open questions, but those yellow questions here are the ones which one can relate quite nicely to g-2, as I want to illustrate in the following. So let's come to g-2. Zooming out a little bit, what we should do is to explain a deviation, which is around 25 plus minus 6 times 10 to the minus 10. So at first, this looks like a very small deviation. However, I want to stress, okay, let's first not stress it right now, let's stress it later. What are the questions that I want to discuss? Which models can explain this deviation? As you will see, it's not completely trivial to explain it, and many models fail in explaining it. Why is this single number so interesting? And sometimes people ask, for instance, journalists, why are you happy that there is a discrepancy between the standard model and experiment? So these are questions that we can come back to. As you know, of course, this is an extremely active area. And in the talk here, I will provide some general remarks, and the examples I give are from our paper, which is a quite extensive survey also from a few days after the experiment. So the important points I want to make are the following. The discrepancy is not small, the discrepancy is large. The discrepancy is almost twice as large as the standard model weak contributions. The weak contributions are 15, the discrepancy is 25 times 10 to the minus 10. But in general, we expect a mass square suppression. Therefore, it's not obvious how you can come up with a BSM scenario which explains the g-2 deviation, but which is invisible everywhere else. And so this is the job that we need to fulfill. The second point is that g-2 has a quite distinctive set of properties which are almost unique. It's a loop-induced quantity. It is CP and flavor conserving, and it is chirality flipping. And so these four properties make it very complementary to a lot of other observables that we have in particle physics. So of course, loop-induced means that we are sensitive to all particles which couple to the muon via quantum fluctuations. And that is complementary to collider observables where we need to produce particles directly. The energy needs to be sufficient. The detectors need to be able to detect the final states. This is not always easy. CP and flavor conserving means that g-2 is complementary to many other observables. It's a dipole observable, and many other dipole observables like EDMs violate CP, or mu to E gamma, B to S gamma violate flavor. And so, of course, it's conceivable that physics beyond the standard model does not break CP or does not violate flavor, and then it would easily contribute to g-2, but not to those other observables. Chirality flips means that the g-2 diagrams need to connect left and right-handed muons, and that makes it complementary to, for instance, electroweak precision observables. And so these set of properties are kind of unique in g-2. And as I said before, we need to find a large effect which is invisible elsewhere. So you can already guess that we need to kind of exploit this complementarity in order to make it possible. And let me illustrate this complementarity just by focusing on this flavor complementarity for a moment, and afterwards coming to chirality flips. So the flavor connection can be illustrated in those plots here, where you assume that g-2 is now explained by some new physics model. And here we choose two supersymmetric models, the MSSM and the R-symmetric supersymmetric standard model that we call MRSSM. So we assume g-2 is now explained. And then we ask, what is the limit that we obtain on flavor violating parameters in the SUSY model from mu to E gamma? Right, because mu to E gamma is a flavor violating dipole observable, which is very similar to g-2, but it involves flavor violating parameters. And so these are the resulting plots. And one of them is from Jeon Park here at KIAS. and the other one was developed more recently by us in Dresden. So we call these traffic light plots. And you see that on the axis you have certain generation mixing parameters in the SUSY Lagrangian. And you get upper limits on those flavor violating parameters of the order 10 to the minus 5 or 10 to the minus 4. And the upper limits are similar in the MSSM and this other supersymmetric model. And I don't want to go into detail, but just let you know that if G minus 2 is explained, then flavor violating observables seriously restrict the parameter space. And you cannot have order 1 flavor violation, but you need order 10 to the minus 4 flavor violation. Similarly, let's look at the lower plot here. This is specific for this minimal R symmetric supersymmetric standard model. Let me not go into detail what the model is, but let me only use this as an illustration of this simple statement. If G minus 2 is large in a model, then you are forced to go into a quite restricted parameter space. And this is illustrated here. So on the x-axis, you have the values of G minus 2. And on the right side of the plot, G minus 2 is large. On the left, G minus 2 is small. And on the y-axis, you have a ratio between observables, namely mu-to-e conversion. That is measured, for example, at the COMET experiment in Japan, and mu-to-e gamma, which we already mentioned before. So two flavor violating observables. And you see that if in general, they are not really correlated very strongly. So, and if G minus 2 is small in this particular model, then the ratio between the two flavor violating observables could be anything you want. It could range from 0 up to a large factor. However, if G minus 2 is large, then you are forced to go into the specific parameter region where the ratio between the lepton flavor violating observables is fixed, essentially. And that is an illustration of going to specific parameter regions. And in fact, so the outcome of this study is that if G minus 2 is really large, then the ratio is fixed in such a way that the COMET experiment becomes almost insensitive to this model. Okay, so you need to go to specific parameter spaces. And now let me come to the necessity of chirality flips, which was another of those 4 specific properties of G minus 2. It's in fact the most important and most distinctive property, I would say, for phenomenology of G minus 2. What do I mean by chirality flips in more detail? So the G minus 2 operator you see here on the right top of the plot of the slide, it connects a left and right-handed muon with sigma mu nu and the field strength tensor. And the prefactor of this effective operator is then essentially G minus 2 over the muon mass. Okay, so this is a dimension 5 operator. Now the point is, and first of all, it's chirality flipping. But the point is, in an electroweak theory, this is not gauge invariant because the right-handed muon is a singlet under SU2. The left-handed muon is part of a doublet. Therefore, in order to write down a gauge invariant version of this G minus 2 operator, you need at least a Higgs vacuum expectation value, like the standard model Higgs doublet vacuum expectation value, or in some new physics models, some generalization of this. But you need some spontaneous breaking of electroweak symmetry. Otherwise, you cannot write down a G minus 2 operator. So, and that means if you look at all the factors that all contributions to A mu or G minus 2 have this very complicated set of factors appearing. So let's go through it. First, from the definition, you get one factor of the muon mass. This comes because the operator gives A mu over M mu. Okay, but then we need from the chirality flip one vacuum expectation value, breaking electroweak gauge invariance. And we need, of course, some fundamental parameter of the theory which gives rise to the chirality flip in the first place. And then you might have all sorts of other coupling constants, and for dimensional reasons, you must get a mass square suppression in the denominator coming from eddy mass. Okay, and so these green factors are coming from the chirality flip, and they are obviously related also to the muon mass generation and they can give rise to significant enhancements. So just to compare it to the muon mass, in the standard model, we would have the standard model Higgs wave and the standard model muon Yukawa coupling, which gives rise to the chirality flip. But in new physics models, the muon mass could arise in different ways, and then g-2 could be strongly enhanced by those green factors here. And I would now like to make use of this structure to illustrate kind of the typical properties of a set of interesting BSM scenarios. So here at the top, you see again the same formula. And below it, you see the formula for the muon mass. And now, just as a side remark, you can also play this game. Let us assume that the correction to the muon mass coming from new physics is actually of order 1. In other words, you explain the entire muon mass by loop effects from new physics. Then, plugging this into the top formula, these green factors become the muon mass itself, and then you would say that g-2 is just given by this small formula on the right, muon mass square divided by the BSM mass without any additional prefactor. So that would be kind of the largest conceivable contribution to g-2 if you require that the new physics corrections to the muon mass are not bigger than the muon mass itself. So you get an upper limit to the possible contributions to g-2. And this upper limit is reflected in the plot here on the bottom by the green line. So the upper limit is such that if you want to explain the current deviation, you can only do it with masses up to around 2 TeV. So it's not a very, very high mass. Okay, but let's now discuss some concrete models and how they behave with respect to chirality flips. First, again, the standard model, electroweak interactions, so W boson loops or Z boson loops. Here, the chirality is flipped in the standard model way, and the chirality flip comes from the external muon line, where the muon basically couples to the Higgs vacuum expectation value and flips the chirality. So we get no enhancement from the chirality flip, and the result is just loop factor alpha times muon mass square divided by W mass square. And from this formula, you get immediately this value 15 times 10 to the minus 10 that I mentioned before, which is smaller than the deviation. An extremely interesting idea for new physics is leptoquarks. Leptoquarks couple directly muons or leptons to quarks, and an example is, for example, leptoquark couples the muon to a top quark. Then what can happen is that you take the right-handed muon, couple it to the right-handed top quark, then the top flips its chirality by coupling to the Higgs vacuum expectation value. The top becomes left-handed and couples to the left-handed muon. So here the chirality is flipped in this very indirect way by basically a product of leptoquark couplings to the left and the right-handed muon and the top quark chirality flip. So working this out, you get a g-2 contribution, which looks like this. You have the two couplings, g left, g right, for the two leptoquark couplings, times the top mass in the numerator, and then just 1 power of the muon mass divided by the leptoquark mass square. So in contrast to the previous case, you do not get muon mass square, but only muon mass to the power 1 in the numerator. So this is an interesting scenario, and for this reason, leptoquarks can give rise to large g-2 effects, even for large leptoquark masses. Okay, then the 2 Higgs doublet model is very well known at KIAS, of course, and its contributions come from those 2-loop bar Z diagrams that also exist in the standard model, where the muon emits a Higgs and the Higgs does a loop, for example, tau loop, and then couples back to the muon. Then we have a 2-loop suppression, but in the type X model, for example, we get a 10 beta square enhancement, but again, a mass square suppression from the Higgs mass here. Then let me also mention supersymmetry. Supersymmetry is also well known, of course, and here the behavior is rather complicated in comparison. So you need supersymmetric partners to all particles, and then the muon can couple to a Higgsino, the superpartner of the Higgs. The Higgsino does coupling to the Higgs vacuum expectation value becomes a g-no, and the g-no couples back to the muon. So effectively, the chirality is flipped by the coupling of the muon to the Higgs-no, then the coupling to the VEV, and then a g-no coupling. And this combination of factors gives rise to the well-known enhancement by tan beta, because we couple here to the vacuum expectation value HU, while in comparison, the muon mass at tree level is generated by the smaller vacuum expectation value HB. So this gives rise to a tan beta enhancement. And looking at the details, you also see that the Higgsino mass is really important. So the Higgsino appears here in the loop. And this, in first approximation, gives rise to the Higgsino mass appearing actually in the numerator as a kind of enhancement. Depending on the details, the enhancement doesn't grow indefinitely, but it is cut off at some point. But in some approximation, you really get enhancements by mu. Then I already mentioned the final possibility, namely radiative muon mass generation, where you just say the entire muon mass comes from loops from new physics. Then you do not get a loop suppression, relatively speaking, in g-2, and g-2 is just given by this ratio, which is maybe the largest reasonably conceivable value for g-2. Okay, and I can mention, of course, that this can be realized in the minimal supersymmetric standard model also if one takes the limit tan beta going to infinity, which was also a study with Jayon here. Okay, let's now look at some examples of concrete models and the constraints acting on them. Let me start with model with the following properties. Let's begin with this question. What model could it be? It has a fundamental new quantum field theory symmetry, which extends relativistic quantum field theory. It predicts the Higgs potential. It predicts the Higgs boson mass in a natural way in the correct ballpark order of magnitude. It contains a dark matter candidate, and it also contains a chirality flip enhancement leading to large g-2. That model is, of course, supersymmetry, or more precisely speaking, the minimal supersymmetric standard model. And the only question is this actually still viable given all the LHC constraints, or has it been excluded or killed by the LHC? So supersymmetry is still very interesting, even though it's not the only interesting BSM scenario. But in supersymmetry, you have all these super partners to standard model particles with different spin. And what is very important for us and in general is that the Higgs sector is supersymmetrized. This gives rise to all these predictions of the Higgs mass and the Higgs potential. And two important parameters come into play, namely tan beta, the ratio of the VEVs, and the Higgsino mass mu. And those are also important for g-2, as we have already seen 5 minutes ago. So here on this slide, again, I show you the Feynman diagram where the chirality of the muon is flipped via Higgsino, g-no, and neutrino exchange. And the numerics work out like this. You get 25 times 10 to the minus 10, which is the deviation that we need to explain, times tan beta over 50, mu over other SUSY masses, and 500 over m SUSY square. So that means if all the SUSY masses are 500 and tan beta is 50, then you perfectly explain the deviation, which means this well-known fact that supersymmetry fits very well to this number. However, the question is whether it is still viable or not. And so here I show you one example plot from our study. And in this plot, you see on the y-axis M1, the Beano mass, which is here the dark matter mass. So it's a Beano like LSP that we have here. On the other axis, we plot the Higgsino mass mu, which is very interesting. And you see from the green area is the region where g-2 is explained. And we fix tan beta to 40. But if we change tan beta, then the green area would even expand further. But anyway, you see here from this behavior that large mu actually increases the range of G-2 explanation. So large hexenomass helps. But for all values of the hexenomass here in the plot, we can explain G-2. In the plot, we also explain dark matter by Stau or lepton co-annihilation, which means that the lepton masses are very similar to the Beano mass in this particular case. That is required by dark matter. Okay, so in case you wonder, what about the LHC limits? So this plot is not affected by LHC limits at all. The entire parameter space here, the two-dimensional parameter space, is completely unconstrained by LHC. And the reason is that we explain dark matter by this co-annihilation mechanism, which gives rise to small mass differences, and the LHC is just not sensitive to those small mass differences. So here we have a perfect explanation of G-2 in a wide parameter space. Let me, however, show you also this plot in order to avoid an uneasy feeling. So what about LHC? So indeed, the LHC excludes a lot. The LHC excludes, however, mainly this g-geno mass M2. So here we plot the parameter space of the g-geno mass M2, where the Beano mass from before is now fixed to some value, 250 GeV. Okay. And in the previous plot, we had fixed the mass M2 to a high value of around 1 TeV, which is, as you see now, so, okay, sorry to say, but the blue region is, of course, excluded by LHC. So in 1 TeV is just above the LHC limits. And in the previous plot, we had chosen 1 TeV or 1.2 TeV, which is above the LHC limits. That is why the entire plot was allowed. So, and but you see that a high value of M2 doesn't no harm to an explanation of G-2 and dark matter. So, but the LHC limits are limits on the values of M2, and values below around 900 GeV here are excluded. However, you see also some other interesting parameter region in this plot, namely very low values of the Beano mass M2 are also allowed. And here in this region, where the Beano mass is very close to the Beano mass, we again get an interesting effect for dark matter. Namely, we can explain dark matter by chargino-neutralino co-annihilation. And again, there we would have small mass splittings, and therefore the LHC limits do not apply. And so these small mass splittings are also allowed by LHC. So we have two distinct regions of parameter space where we can explain G-2 and Beano-like dark matter at the same time. Let me spend maybe a few moments on supersymmetry in general. So we did a very extensive and broad analysis of the MSSM overall. And I would like to flash you all the plots that we did. We have 7 plots, and here is a very general overview, which just illustrates that explaining G-2 requires specific light SUSY masses. Okay, this is kind of obvious, and so but this plot quantifies what we actually need before replacing LHC or other limits. So the trick is that you should look at the lightest muon mass on the y-axis and the heaviest chargino mass. If you look at it in this way, then you can make a full scan of the MSSM, and you see that in order to explain G-2 at the 1 sigma level, you have to be in this parameter region, which means, for example, so here the black vertical line denotes the LHC limit, the best possible LHC limit on chargino masses of 1.1 TeV. This is the highest LHC limit found at all under certain conditions. And the highest limit on lepton masses is around 700 GeV. So you might say, okay, let me avoid the LHC limits and let's assume leptons are above 700 and charginos are above 1.1 TeV. Then you are in this rectangle here at the top right. This rectangle at the top right naively avoids all LHC limits in the most trivial sort of way. You are just above all LHC limits ever found. And then you see that g-2 is definitely too small no matter what. Therefore, you need to be in some parameter space where LHC limits actually exist. So you need to be either in this rectangle where both leptons and charginos are kind of below the maximum LHC limits, or in one of the other where either the leptons or the charginos are somehow below LHC limits. That means you need to be in some tricky parameter space where you evade the LHC limits, for example, by small mass splittings. So this is the general kind of picture. And now let us look at the 6 detailed plots. But don't worry, I will not go through all the plots in detail, but let me just give you the overview kind of picture. So what do we do here? We can first of all categorize the SUSY or MSSM parameter space into the different dark matter candidates or the different LSPs. So in the left column of plots, we have Beano-like LSP. That means dark matter is really fully explained by a Beano-like LSP. And that is what we already discussed. We can do it either using lepton or Stau co-annihilation, or we can do it using chargino-neutralino co-annihilation. And in all these cases, we can perfectly well explain g-2, and the LHC limits can be evaded because of the small mass splittings. In the middle column, we have Wino-like LSP or Higgsino-like LSP. And in those two cases, actually, we can explain g-2 very well also. And in particular, in the case of Wino-like LSP, you see almost the entire plot is green, which means Wino-like LSP is really excellent to explain g-2. Higgsino-like LSP can also do it in a particular parameter region. But in those cases, we cannot explain dark matter at the same time because the relic density is too small. So that is not forbidden, but we need an additional dark matter candidate on top of the LSP from the SUSY model. But this is also viable. And in those two plots here, we also assume that the mass gap between the leptons and the LSP is rather small, so that the LHC limits on the leptons are evaded. Then on the right, we take a final different, let's say, region in the MSSM parameter space where we say that now the leptons are rather heavy and both charginos are lighter than the leptons. So this is kind of complementary to the previous 4 plots. And if both charginos are lighter than leptons, then the LHC limits on the charginos are not very stringent. So in these, in particular in the lower plot, there are essentially no LHC limits at all. However, there are still significant LHC limits, limits from dark matter constraints on the parameter space. So in those cases where both charginos are lighter than leptons, it is not easy to explain g-2, even though there are corners where it works, of course. So the general picture is that the SUSY parameter space is wide open and has a lot of regions where g-2 can be explained, even a lot of regions where g-2 can be explained simultaneously with dark matter. But in all cases, we are led to specific mass patterns between the SUSY particles, which are now interesting and can give us clues on model building, on SUSY breaking scenarios, for example. The co-annihilation definitely helps. So once you explain dark matter using co-annihilation, you automatically have an easier task to evade LHC limits and can then also explain g-2. But there are also negative statements. For example, the well-known constraint MSSM, where you put in some constraints from gut ideas, that is excluded as an explanation of g-2, which of course also is a nice result that you can make progress in step-by-step falsifying scenarios. So much for supersymmetry. Let me now explain or switch gears a little bit What we also did was a kind of systematic analysis, going step by step through all possible extensions of the standard model, just organized by quantum numbers and putting in new fields to the standard model. So we cover 1 field extensions, 2 field extensions, 3 field extensions, just organized by the quantum numbers. We always require renormalizability, and we only looked here at spin 0 and spin 1/2. So we did not consider here, for example, Z prime models, although they are, of course, also interesting. But let me focus on the results from this particular analysis. And so among the 1 field extensions, you see here a Leptoquark Feynman diagram. This is something that works. Leptoquark is just 1 field which couples to standard model particles and gives rise to large g-2. However, in general, if you go through all possible quantum numbers of 1 field extensions, then most of them, or at least let's say many, cannot accommodate the current g-2 value, because either they automatically only give negative contributions to g-2, or the contributions must be very small because of LHC limits. And in particular, they are usually too small if there are no chiral enhancements. And so what models do you need in order to get chirality flip enhancements in a 1 field extensions? The only 2 possibilities are, in fact, Leptoquarks and the 2 Higgs doublet model. These are precisely the 2 possibilities for enhanced chirality flips, and Leptoquarks and 2 Higgs doublet models actually are the only possibilities among those renormalizable 1 field models. And you see here a sketch of a table with red and green entries for excluded and non-excluded 1 field models. We have 1 additional fermion, 1 additional scalar field. If we have this, then the chirality can never be, chirality flip can only be done at the external muon line. There cannot be a chirality flip enhancement from the U physics. And therefore, the g-2 contributions from such 2 field models are always small. In order to get significant contributions, you are forced to go to small masses of the models, and then you have, of course, very strong constraints from colliders. Therefore, here there are even fewer possibilities than in the case of 1 field extensions. 3 field extensions open up dramatically the range of possibilities, and 3 field models, with them you can essentially do everything. And supersymmetry is actually an example of 3 field models, because the Feynman diagrams, which are relevant for g-2 in supersymmetry, involve precisely 3 fields. And but in general, 3 field models can also be investigated without supersymmetry in the background, and then you can see that you can nicely explain g-2 and dark matter simultaneously via new chirality flips. Let me show you 1 plot for Leptoquarks here on the left. And this Leptoquark scenario is one where the muon couples indeed to the left-handed and to the right-handed top quark. So you need specific quantum numbers for the Leptoquark such that this works. And once it works, you can get this very huge chirality flip enhancement from the coupling to the top left and top right. And here you see the resulting plot. You explain g-2 in the green region, and the gray vertical band is excluded by LHC, because LHC constraints on Leptoquarks are strong, since Leptoquarks are strongly interacting. So the LHC limit is around 1.3 TeV, but above this value, you can nicely explain g-2. And so actually there is a wide open parameter region. Now let me just mention the blue area here is not excluded by experiments, but the blue area is excluded by this argument that we do not want that the new physics contributions to the muon mass are larger than the muon mass itself. So if we imply or apply that criterion, then the blue region is excluded. But you shouldn't use that as a hard cutoff. It's an order of magnitude limit from this kind of fine-tuning argument. Anyway, the Leptoquark model can explain G-2 very nicely. On the right, you see an example of such a two-field model. We call it Model L, so it's a no-name model. It is one of the very few models which have any chance of working, and it does not give rise to a chirality flip enhancement. Therefore, you need very small masses of the order 1 or 200 GeV in order to explain G-2. And we investigated systematically all these viable two-field scenarios, and the outcome is that it is impossible in all of those to explain G-2 and dark matter simultaneously. So this model has a dark matter candidate, but the parameter region you need for dark matter is different than the one you need for G-2. So therefore, our result is that if you want to explain G-2 and dark matter simultaneously, you need at least 3 new fields. Let me also comment on the 2 Higgs doublet model, which is of course extremely well studied by Jin here at KIAS. And in particular, he pointed out a long time ago that the type X version of the 2 Higgs doublet model is a prime candidate for a G-2 explanation. We, or I show here a further generalization of this, the so-called flavor-aligned 2 Higgs doublet model, which contains type X as a special case or a subset in parameter space. But anyway, the 2 Higgs doublet model is, of course, a very nice model which implements the idea of a richer Higgs sector, and it involves also a rich new Yukawa sector. The G-2 value can be explained by those bar Z diagrams again, where the muon exchanges a Higgs, the Higgs couples to a loop, either tau loop or a top loop in this case, and then we get particular values for G-2. Now, in this flavor-aligned model, you get larger contributions to G-2 than in the type X model, because we allow simultaneously that the new Higgs couples not only to leptons, but also to top quarks in this particular case, for example. And so if we maximize the couplings to leptons and to top quarks or other quarks at the same time, then we can maximize the contributions to G-2. And then obviously there are constraints from LHC, because if the new Higgs couples to top quarks, then we can produce it via gluon fusion at the LHC, and then it decays visibly into taus. So this is an observable process, but it has not been observed. Therefore, we get upper limits on the couplings. And from those upper limits on the couplings, we can derive an absolute upper limit on the G-2 value in this flavor-aligned 2 Higgs doublet model. And of course, one can also derive an upper limit in the type X model, which is then a little bit smaller than this. So here you see this upper limit. It's just at the same order of the currently observed deviation. So we can still explain G-2 in this model in a parameter region where the new Higgs is a bit below 100 GeV. But it's just about possible. And if the future deviation becomes a little bit larger or the LHC constraints become a little bit stronger, then this model might be excluded as an explanation. So let us now draw some general conclusions from all of this analysis and from the many examples that I have shown you. What are the general points that I would like you to take home, or what are my own general conclusions? So we started with looking at these open questions of the standard model: dark matter, origin of Yukawa matrices, origin of electroweak symmetry breaking. And they are now connected to G-2. So why is G-2 connected to dark matter? Very obviously, dark matter is by definition hard to see in detectors. But of course, dark matter could couple to muons, and that means that dark matter is a very good way to give rise to large effects in G-2, which are hard to see elsewhere. And indeed, that is the simple explanation why so many examples exist where G-2 is explained using dark matter particles. Supersymmetry is an example, but there are also many other examples as well. In our study, however, we found that indeed this is restricted, and we need at least 3 new fields in order to make it work. dark matter and g-2 simultaneously. So, and in general, direct detection constraints on dark matter are important, and we need to take them into account. So the other connection that I would like to make is to the muon mass generation mechanism via those chirality flips. And so this is, of course, really maybe the most distinctive feature of the quantity. So let's just explain this once again in this more pictorial way. So in many experimental talks on g-2, you see this, that g-2 is a continuous spin rotation compared to the axis of momentum. And so such a continuous spin rotation is only possible if the particle has a rest frame and a non-zero rest mass. In the rest frame, really, you just have a continuous spin rotation. If you compare it to a photon moves at the speed of light, has no rest frame, and the spin of the photon is the helicity, can only point forward or backward, but the photon helicity can never have an angle. So in order to make sense for g-2 at all, we need a rest mass, and this is the reason why we have this deep connection between g-2 and the muon mass generation mechanism. And of course, the muon mass arises in this very complicated way in the standard model by coupling the muon via Yukawa matrices to the Higgs field, which in turn is generated from the Mexican head potential. So, and of course, open questions are related to all of these things, and new physics models can dramatically change the Yukawa structure, can dramatically change the Higgs potential. And if it changes it, then new physics models can easily give rise to large effects in g-2. And that, of course, means in turn that g-2 can really be a probe of those ideas for extending the Higgs or Yukawa sector. And so we can now come back to those questions that I asked before. We know we need a large effect, and we need to exploit all of those complementarities. And so we can come back to those questions which I asked in the beginning: which models can explain the deviation? And we see many models can explain the deviation: SUSY, 2x doublet model, Leptoquarks, and so on. So there are many models, but in all of those models, you need to go into specific parameter regions. So in SUSY, you need specific mass patterns. In Leptoquarks, you need specific Leptoquarks which couple the muon to the top left and top right simultaneously. And in the 2x doublet model, you are forced to a region with specific small Higgs masses and so on. And of course, that makes this single number so interesting because it's not easy to explain. And any explanation typically involves very interesting, deep features. And that makes us happy because we might now make really significant progress if the deviation gets confirmed in the future. Let me flash this slide without going into any detail. This is a list with green and red items for excluded and viable scenarios. But let me just summarize. So we see that g-2 is a large discrepancy right now, larger than the weak contributions, and that is why new physics explanations need special properties. g-2 is loop-induced CP and flavor conserving and chirality flipping, which makes it complementary to many other observables. And thinking about this, we see this connection to dark matter or to chirality flip enhancements which make g-2 a window to the muon mass generation mechanism. As I said, many models can explain the deviation, but many other models are also excluded as possible explanations, like constrained MSSM, 2 Higgs doublet model type 2, and so on. All of those are already excluded. But even for the viable remaining models, there are important experimental constraints. Currently, we see that particularly important constraints come not only from LHC, but also from dark matter direct searches. And they are improving in the future, so that is very promising. And from the structure of the models, you can also see that many other experimental tests are possible, like Higgs coupling measurements are important. Obviously, they also test the muon mass generation mechanism. B physics measurements are important. Charge lepton flavor violation measurements are important. EDM measurements, light particle searches, and ultimately, it would be fantastic to have E plus, E minus, or even muon colliders to further test and maybe discover those particles relevant for G-2. So 20 years after Brookhaven first observed this interesting and tantalizing deviation, and after so many developments in theory and in experiment, now the deviation has been confirmed. And this is only just the beginning of this new era of Fermilab G-2 measurements. And the era starts in a very promising way. We have the best possible starting point where all the experimental determinations are consistent with each other. And so we can look forward to more accurate pinning downs of the deviation and look forward to investigating this also in scenarios for physics beyond the standard model. So thank you very much for your attention.
Thank you very much for the detailed talk. Are there questions or comments?
Hello, I had a couple of questions. First, you mentioned the how to estimate the near field contribution in a rule of thumb, but is there? I'm wondering about the interference, the sign, relative sign of the interference. Is there any simple way to see the near field contribution is constructive or destructive interference?
Right. Okay, thanks. That is a very good question. So in fact, as I said briefly, in some of those models, the sign is fixed. And sometimes the sign is negative and then the model is excluded, of course. And in some other cases, the sign is positive. And in some cases, like in supersymmetry, the sign can be positive or negative. And so the very simple thing is, if you have these chirality flip enhancements, like you do in supersymmetry and in many other models, then you typically have a new parameter, like in this example here, you hypothetically have two new fermions, a new chirality flip. Then this green dot is a new parameter of the Lagrangian. And the new parameter would be able to be positive or negative. So in such models, the sign can be anything you want, and it depends on the sign of this new physics parameter, which is typically a mixing parameter, and both signs are equally plausible, let's say. So in those cases, you can have either sign, and of course, you can fix the parameter such that the sign comes out to be positive. In contrast, if you have a scenario where you have no additional chirality flip, like in the right diagram here, then you have, for instance, two new particles, and both vertices are now coming from the same term in the Lagrangian. Therefore, this coupling appears squared, and you have no way to change the sign. The sign comes out, whatever it is, either positive or negative, and then the sign typically depends on whether the photon couples to the fermion or to the scalar, and it depends on the electric charges of the fermion and the scalar. So let's say simple-minded picture, you have scalar with charge 0, fermion with charge 1. Then the sign is something. Scalar with charge 1 and fermion with charge 0, the sign is something. Sometimes we have charge 5/3, the other has -2/3, and so on, and then you get a certain sign of the overall effect. But in such cases, the sign is always fixed.
I see. Thank you. And also, so you're saying that many models can explain mean G-2, but many models are also excluded by some other experiments. But what kind of experimental data do you think the most severe, give a severe constraint?
Okay, all of the experiments are important since all the models are so different. So I mean, that is why I cannot give a completely general answer. But the multitude of all the experiments is, of course, important. But as an example, let us look at this extremely simple model. I cannot flip the page right now. Ah, here it is. So this simple model over here on the right, this is a model with a no-name model with just 2 new particles. And here the LHC constraints are, of course, very severe. LHC constrains the masses of those new particles. And g-2 requires the masses to be small. And that is only possible if you evade the stringent LHC limits, and you can evade them by having very small mass splittings, because the LHC becomes insensitive if you have small mass splittings. So you have a dark matter particle, which is invisible anyway, and another particle which is close in mass, and then the LHC is insensitive, and that is why you have this small diagonal window where the LHC allows the model to survive. And so, and then it just happens that in this particular case, in this small window, the dark matter relic density is too small, and therefore you cannot explain it. So here, dark matter relic density becomes small because the couplings are large, masses are small, so you have large annihilation cross sections, and that is why the dark matter relic density becomes too small. So it's details like this which rule out the models. But in general, LHC is definitely important, and for some low mass models, also old lab data are of course very important. And but particularly the combination with dark matter and sometimes other experiments are important. So in those cases where you have new flavor physics, like leptoquarks involve, of course, flavor structure, 2x doublet model involves flavor structure, then always the off-diagonal flavor elements are constrained strongly by other flavor experiments, of course. But then if you reduce the flavor structure to diagonal matrices and so on, then the flavor constraints are all evaded. And what then remains are constraints from dark matter and LHC and LEP.
I see. Thank you.
Maybe I should just mention this just as an additional comment. Jin knows this, of course, and the 2x doublet model is an example of that. So sometimes these not so well-known experiments like tau physics measurements, tau decay, or LEP measurements in lepton universality and so on. So they are not always on our agenda these days, but they provide important constraints also in the 2x doublet model. In particular, tau physics places extremely important constraints on the parameter space, which explains g-2.
Okay, Dominik, so can you comment on lattice results?
Okay, the usual.
The recent BMW. So
yeah,
what is your opinion?
Right. Yes, okay. Do I have a backup slide on it? I might. Here a backup slide. I copied from Thomas Teubner, who is in the steering committee of this theory initiative. And so just that we have it visually in front of us. So of course, the lattice results are extremely promising. And you see here this blue cloud of data points from the different lattice calculations. And the new lattice result that everybody is talking about is this BMW result here, the second from the top, which has a much smaller uncertainty than all the other lattice results. And the current result which is used for the standard model prediction is the gray one at the bottom, coming from these dispersion relations. And okay, so the first statement to make is, of course, that the lattice result is making really a tremendous progress, and this is extremely promising. But what you also see is that there are many different lattice groups working worldwide on this problem. And so far we have one result which is more precise than the others, and we need cross checks from the other groups because they use different lattice discretization methods leading to different systematic uncertainties. And those uncertainties that you see are actually systematic uncertainties, not statistical ones. So one really needs to scrutinize what the numbers mean and what the lattice ultimately comes up with. But of course, this is ongoing, and there will definitely be progress in the next 2 years on this. And then the lattice might or probably will become competitive also with the dispersion relation analysis. Then sometimes the claim is made that the BMW result on its own makes the deviation between standard model and the experiment disappear. But I would dispute that statement in two ways. First of all, the discrepancy is not zero. Even if you take the BMW result 0, it lies exactly in the middle between the previous determination and the experiment. And then we will have to see what happens if the uncertainties become smaller. But the more important statement is that really you cannot ignore the traditional dispersion relation results, because they are based on rigorous quantum field theory. The dispersion relations are exact relationships coming from relativistic quantum field theory, and the data points which go into those dispersion relations are measured in a multitude of different experiments, which also have been cross-checked over decades, in fact, using different experimental techniques. So there is really a lot of knowledge and a lot of cross-checking going into this. And here in these gray determinations, the uncertainty is really an experimental uncertainty. So it's actually better controlled. It's not a systematic uncertainty. It's an experimental uncertainty, to a large extent statistical uncertainty from those different experiments. The dispersion relation is exact. So this is a true, rigorous standard model prediction. So even if lattice results show something different, then what remains is that we have here a rigorous standard model prediction, which has a 4.2 sigma deviation from the experiment for G-2. That doesn't go away by any lattice calculation. What needs to happen is, of course, we need to understand what is the relationship between the lattice results. First of all, the lattice results need to find some unambiguous prediction, which ideally must agree with the dispersion relation results. But if it doesn't agree, but this is now speculation, if there is a discrepancy between two different standard model evaluations, then that must be clarified, of course, internally. And but as long as nobody is able to point out an error in the dispersion relation calculation, then this result stands, and it deviates quite significantly from the Fermilab measurement. But one should also say that not only the lattice is making progress, also the dispersion relation is making progress, because also there are further experiments measuring those E plus E minus data, and of course people are still continuing to scrutinize the methods that they use. So also this will become more accurate and also scrutinized in the future.
Yeah. Okay, thank you.
Hello, Dominik.
Hello.
Hi. I was in another meeting, and so I could listen to your talk only the last 2 slides.
Okay.
Yeah, even if, but I mean, I could see your screen, but they could not hear your voice. So could you show this slide for hadronic vacuum polarization in the very beginning?
Okay,
Yeah.
so this is of course a more extensive slide on vacuum polarization from Thomas Teubner. My own slide is much simpler, and it takes a while to scroll. These pictures are very large files. Here, so this was my slide on vacuum polarization.
Here, are you showing this data from? You are showing data from 600 MeV, right?
Mm-hmm.
And how about the below the 600 MeV? You are still using that, but it's too small.
Okay, this is just an example plot. I took this example plot also from Thomas Teubner, which is the plot of the data region, which is particularly important and particularly crucial it gives a large contribution to the g-2. However, there is of course data for all energy ranges, but the most important one is e plus e minus 2 pi pi, and there is this resonance at a rho peak or rho peak resonance, and in this region the data points are particularly important, and that is why I selected this. And here you see it's almost invisible, but this is this set of many different experiments measuring those data. So there are measurements using radiative return from Barbar, for example, and Chloe. Barbar is green here, which uses the radiative return technique, and many of the other data points like this CMD2 and SND, they are these Novosibirsk experiments using direct energy scan methods, which are done in an entirely different way and use different Monte Carlo theory programs to analyze the data and so on. So that is why I said there is a multitude of different experimental techniques also involved in extracting this data. And such experiments are now also ongoing, and so the quality of the data will further improve.
Okay, so maybe I think I can ask you by email later more. And you talked about the Leptoquark models. So what is the minimal set of Leptoquarks if you want to explain muon g-2 and also RD anomaly, RK star anomaly, all of them?
Right.
Also, assuming they are all anomalies.
Yes. There is a certain set of Leptoquarks which can do it, and the ones that I showed cannot explain the B physics anomalies. What I showed was spin 0 Leptoquarks, and they cannot explain RK and RD. But what you need in order to explain those is spin 1 Leptoquarks. At least with spin 1 it works. With spin 1 Leptoquarks you can explain the B physics results, and I'm not absolutely sure, but I strongly believe from remembering the appropriate papers that you can explain g-2 and also the B physics anomalies by imposing several Leptoquarks of different kinds. So as far as I know, it's not possible to explain all the B physics results and g-2 simultaneously if you postulate only one single type of Leptoquark. If you postulate several types of Leptoquarks, then you can definitely do it. So I remember exactly one paper where they had an elaborate scenario which was motivated from some new gauge symmetry, and in that scenario they had spin 1 Leptoquarks and spin 0 Leptoquarks with flavor matrix valued couplings, and then by tuning the parameters of all those flavor matrices they could accommodate B physics and g-2 simultaneously.
Do you remember the author? Do you remember the authors of this paper?
Yes, that was Peter Stangl and collaborators.
Steiner?
Stangl and
okay.
Yeah.
And sorry, one more question. And could you show the g-2 in MSSM, I mean in SUSY models?
So here this was
the beginning. Here so here in this plot, do you impose the lightest neutrino being the dark matter of the universe?
Yes.
I mean, with the correct relic density?
Yes.
And what is this pink, or what is DMDD?
Dark matter direct detection constraints. So these are constraints from dark matter direct detection experiments. So we used here xenon 1 ton, and that excludes this red strip in parameter space. So the direct detection constraints have mainly the effect that you get a lower limit on the Higgs mass mu. So if the dark matter mass is here between 200 and 500 GeV approximately. And what we find is that the direct detection measurements rule out that the Higgs mass is equally light as the dark matter mass. So there must be a significant mass gap between the dark matter and the Higgs mass. Roughly speaking, it's a factor 2. And you see here the exact values that you need.
Okay.
So, and interestingly, we also looked at this case where we had opposite LSP, so we know LSP or Higgs LSP. And in those cases, you might know that in order to explain the relic density, we need rather high masses of the LSP. For example, Higgs LSP can explain dark matter if the Higgs mass is 1 TeV approximately. So if you have this, then you cannot explain G-2. So we looked at the case of Higgs LSP and explanation of G-2, and then you need small Higgs masses of a few hundred GeV. The dark matter relic density is then always too small. But we said this is not excluded. We just need to hypothesize an additional dark matter candidate. But interestingly, even then you get constraints from this dark matter direct detection. So even though the relic density is too small, the direct detection constraints are severe, and you need, again, a mass splitting between the Higgs and the gauge.
Okay, thank you.
What happens if the new particles responsible for the value are light particles rather than heavy particles? Do your general lessons still apply, or how do you have to modify the reasoning?
The general lessons, okay, we didn't explicitly investigate this case, but that is obviously very interesting too. What is clear is that if you have very light particles, meaning below 1 GeV, of course, then automatically you can only have neutral new particles, obviously. And then you are down to either neutral scalars or neutral new gauge bosons like Z prime or dark photon. And so we didn't do a dedicated investigation of dark photons or Z primes, but of course there are many papers on this, and depending on the Z prime quantum numbers, you can explain G-2 as well for rather light Z prime masses. So as I mentioned briefly, we mainly looked at cases of spin 0 and spin 1/2 that obviously doesn't include Z primes. We did a small review of the situation of Z primes in our paper. So as you might know, this quantum number L mu minus L tau is really a very interesting quantum number for Z primes, because here, first of all, have an anomaly-free quantum number. And second of all, the Z prime would couple only to muons and tau leptons, not to electrons. That is why you can have rather light Z primes without violating other experimental constraints. So this is an interesting scenario, and it is viable, and it's also regularly being studied these days. And by the way, just B physics came up before this Z prime with this sort of quantum number. There were papers. I think the paper that I mentioned already has also this Z prime. And on top of that Z prime, there are leptoquarks with spin with various spins, and then you can accommodate G-2 and B physics as well. But for G-2 alone, let me finish this point. So if you want very light scalars, then very often what helps is non-renormalizable operators, like, for example, axions. Axions or axion-like particles are, of course, very interesting. And they can also explain G-2, but we excluded them from our analysis because they couple via dimension 5 operators, which is non-renormalizable. But that works as well, and that is very interesting.
Sorry, let me ask one more question. So in the middle of your talk, you're trying to connect, I think you're trying to connect this muon G-2 and radiative generation of muon mass. And did you discuss any concrete model, or I didn't? I couldn't. So
yeah,
you have.
I mentioned our concrete scenario from the MSSM with 10 beta infinity.
Okay.
So that was this kind of neat idea that in this limit of the MSSM, actually the muon mass is 0 at 3 level, because the vacuum expectation value VD vanishes, but the muon mass is then generated via loops. So this is one possibility, but of course there are many others, and but I didn't speak much about them.
I see. Okay, thank you.
Are there
Dominik, sorry, I wanted to ask a very naive question, because I don't know if there will be a new kind of experiments from which you could extract this hadron vacuum polarization, you know, in order to check. So I don't know if you talk about that.
There is this extremely interesting idea, mu on E, where they will do a measurement at low energies at CERN, muon electron scattering. And the idea there is that they are sensitive. Let me show the picture of the vacuum polarization. That one is sensitive. You see, in this dispersion relation, what you do is you are sensitive to the hadronic vacuum polarization, and with an energy or a Mandelstam variable S, which is positive. So the Q square which flows through the blob is positive. So time-like region, as they call it. And an alternative way to determine this would be to use, as they call it, space-like Mandelstam variable. So you would need a process where this hadronic blob appears in the T channel. And this would give rise to an entirely different determination. And in this muon electron scattering, this is what one can do. So they want to do muon electron scattering, then they scatter via photon exchange in the T channel, and then by measuring this scattering extremely precisely, one becomes sensitive to the hadronic blob in the photon propagator in the T channel. So the idea there is that one directly measures this hadronic blob using T channel exchange processes. And that would give a third way, in a way, to determine the hadronic vacuum polarization. It's complementary to this dispersion relation with time-like data, and it's obviously also complementary to lattice. So if this is done, that would be an extremely interesting cross-check of the current methods. And I think this was always a plan. It was not yet clear whether it will be done at CERN, but given the current situation, I think this is extremely well motivated. And of course, on the other hand, as I said before briefly, so you see here all these small experiments in the almost invisible data points, CMD2, SND, and so on. So there will be always new experiments, CMD3, for example, and successive experiments of SND, and also of the BESS experiment in China. So they will also improve these data points down there.
Maybe this is an unrelated question, but do you have any comment on electron G-2?
Electron G-2 is, of course, now gone away, essentially. So as you know, there used to be a small discrepancy of 2 sigma, which was mainly interesting because it had the opposite sign. So it presented a kind of nice exercise for theorists to come up with BSM explanations of a positive G-2 of the muon and negative G-2 of the electron. And of course, people came up with explanations which were not maybe too compelling, but anyway, now the deviation is basically gone away. But we will see how it further develops in the future. So it hinges on the measurement of alpha, the independent measurement of alpha, and the measurement of g-2. So all of this will also further improve in the future. So g-2 of the electron is something to keep an eye on, definitely. And of course, the ultimate question, if anything, is there this naive scaling between g-2 of the muon and the electron? So naively in flavor blind models, you would get muon mass square over electron mass square as the ratio between the two effects. So ultimately, if g-2 of the muon is non-zero, really, as we see here, then we would expect that g-2 of the electron is also non-zero, but the effect should be 40,000 times smaller. And it will take a while until the experiments are sensitive enough for that. But once they are, we could do this test. Is the g-2 of the electron really exactly 40,000 times smaller, or is the ratio something else? And then we learn something extremely important about the flavor structure of new physics.
Okay, thank you. Other further questions or comments? Okay, if not, let's thank Dominik again.
Thank you very much for the
Thank you.
invitation.
Thank you.
Thank you.
Bye.
Look,